my distinct pleasure to introduce again my old IEEE colleagues, Dr. Venkatesh Ramaswamy. He goes by Venki. He'll be talking about Open RAN MEC-enabled network as a service platform for spectrum sharing scenarios. He's also been a frequent speaker. He's a distinguished chief technologist for NEXT at MITRE. Leads many R&D activities. He's also been heavily associated with ATIS, NEXT Alliance, published more than 50 peer-reviewed publications, and program committee members for various IEEE conference, got PhD from University of Mississippi. With that, Venkat, welcome. You got 20 minutes.
Yeah. Thank you.
Thanks. Sam, you may like to change to slide.
Okay. First of all, thank you so much, Ashutosh, for the opportunity to be here. I am going to start with something that we all know. Spectrum is a very precious resource. And spectrum, especially in the lower bands and the mid-band, is even more precious. Why? Because it has the right amount of coverage and capacity. The problem comes when the lower band and the mid-band, it's already occupied by several federal systems, and it may not be very economical and efficient to relocate them. You might think that the problem is only in the lower bands and mid bands, but also in the higher bands. We have several scientific users occupying those bands, and having a contiguous band for commercial system may not be feasible there. So on the right-hand side, you can see a very simple extrapolation chart where we have shown on the x-axis different generations, and the y-axis the amount of spectrum that is used by the commercial systems. You can see a significant increase, specifically 88% increase over generation. So every generation needs around 88% more spectrum than the previous one. And what is shown here is that by 7G, about 93% of the whole spectrum within the 6 gigahertz band is going to be needed for the cellular systems, which is really unsustainable. And the only way we can solve this is by sharing. So sharing between the incumbents and the entrants, which are really the communication systems, the cellular communication systems. There is also another solution to this problem, densification, but as you all know, densification is going to be very costly, right? Adding more base stations will not only increase the cost, but it also is going to increase the carbon footprint and so on. So the only realistic way to meet this demand is to have the incumbents, which are typically the federal systems, share the spectrum with the commercial systems. And there is some good news here. There is some hope here, because the entrants, which are the 5G and the 6G systems, they come with all sorts of sophisticated techniques that allow you to share with the incumbents that may or may not be very sophisticated. So that is the hope here, and that is going to be the focus of this talk today. Now, if you want to share the spectrum, as I said, between incumbents, federal systems, and commercial systems, we think that there are 3 important aspects that need to be taken care. One is that the entrant needs to discover the presence of an incumbent. So that's the discover part. Once that part is done, it needs to decide what to do, right? So it needs to decide what actions the system has to take. And once that action is taken, it has to actually decide or actually do that, right? It has to actually implement the controls, implement the configuration that is needed to achieve that coexistence. So any efficient spectrum management would have these 3 components, where the system itself will have to get the situational awareness of what is happening within the environment, and then it will have to decide on what to do and finally do it. So this is the 3-part discover, decide, do framework that we think is very important in any efficient spectrum management activity. Now, in 6G, there is this new feature called as the integrated sensing and communication. And the reason why I want to talk a little bit about this is because there are aspects of this feature that can be used for the previous slide that I was showing, where we can use this feature and implement some of the aspects that we are talking about in the situational awareness part. So how can we use this sensing and communication feature that is going to be available pretty soon and make the communication systems also do the sensing part? Because having a separate network for sensing may not be very desirable, may not be very efficient. So that is what I'm going to talk a little bit about here today. And as it stands in the standards in release 19, there are two models, two specific things that are being talked. One is what they call as a collocated 3GPP system, where the sensing transmitter and the sensing receiver are collocated. So your base station is sending a signal, and based on what it receives from the reflections and so on, it's able to get a sense of what is happening in the environment. So that is what is shown on the left-hand side. And they also have something called as a non-collocated. I have this. I have the non-collocated 3GPP system, where the transmitter and the sensor, the sensing receiver, they are not collocated. So there are two different base stations, for example, and one of them is transmitting something based on the reflections that it receives from an object. For example, the reflections can be sensed using at different base stations or at a different base stations. So that's the non-collocated part. And if you are from a radar community, you would immediately see this as a monostatic and a bistatic configuration. However, what is not covered in the specification is the fact that the signals can be non-3GPP signals, right? So for example, if it's a Wi-Fi signal, can you actually do this? That part is not really covered in the standard. But the good news is that the architecture that is being talked about, that is being discussed in this specification, is readily available, readily transferable to a system where the 3GPP signal or the reflected signal is non-3GPP. And that's exactly what we will use in the activity for sensing. So as I said, the first part of the spectrum management activity is the discovery part, right? And the discovery could be done using an external sensor network. If you are aware of the CBRS, they have what is called as the external sensing capability. However, that is very expensive in terms of having a separate network. Also, you have to protect that sensor itself, and that is going to exclude several users from actually using the system. So a better way could be to use your communication infrastructure as a sensing capability as well. So if we are able to use this structure, use the configuration, use the architecture that I showed you in the previous slide, but modify it to sense signals that are non-3GPP, then we can readily accomplish the task that is shown on the left-hand side, which is the discovery part. And that's exactly what we are trying to do here. So as I said, having an external network is going to be very expensive. So the idea would be to use something that is already available, which is a base station, and use the base station as a sensor in addition to being a communication infrastructure. This would allow having no whisper zones, because that is one of the drawbacks of having a separate networks, because you need to protect that network as well. Now, if you are using communication infrastructure as a sensor, the first part of that is to convert your G node B as a sensor, right? So once you have a G node B as a sensor, you will need multiple G node Bs to make the network itself as a sensor. So the first part is to convert that G node B itself, the base station itself, as a sensor. And there are a couple of different ways you can do this. And you will see this in the later slide that you don't have to fix on one particular method. You can use multiple of them at the same time. The left-hand side, what you see there is that Gnode B already has a lot of information. The scheduler in the Gnode B, which is the brain of Gnode B, has pretty much everything that you want to know. It has information about all the users, the channel that they are seeing, and it is so sophisticated that if you are able to get information about the scheduler, how it works, then you are able to get information on the sort of interference that the Gnode B is experiencing, and that could be used for your advantage. So on the left-hand side, what I'm saying is that if there is interference present because of an incumbent, typically the scheduler would schedule around the interference, and you can see that by just looking at the activities of the scheduler, you are able to figure out the presence of an incumbent. It doesn't work all the time, because if you have a lot of data that is being transmitted, the scheduler may not be able to schedule around. It will still schedule in a spectrum, in a band that is heavily interfered with. The second aspect, so this is, as you can see, there is no real intrusion here. Intrusion in the sense, no real change in the activities of the scheduler. We are just looking at how the scheduler is operating and then making sense out of the presence or absence of an incumbent. The second one is a little bit more intrusive way, where we are using some of the resources set aside for communication, and we are using that for sensing. So in this case, what you can see is that for a TDD-based system, some of the slots that you are using for uplink can be now used for sensing. So let's say that you have 10 slots, and you are using 1 or 2 slots for sensing. So those slots will now will not be available for communication. So that's what is shown there. Advantage, you have a very latency sensitive way of doing things. You have much more predictive way of doing and sensing. However, the drawback is that now your communication system performance is going to degrade. Why? Because you are using some of the resources for your sensing. So there are 2 different approaches that you can employ within a Gnode B to make it as a sensor. So Gnode B as a sensor can be done. Now we are going to, next couple of slides, I'm just going to focus on the second part, which is the near real-time sensing, which is using this intrusive way, which is adding the sensing capability to an existing communication. And these 3 slides are going to be more implementation focused, okay? So the first one is when you are able to offload all your IQ samples, for example, or the samples that you get from the RU to a capability like a MEC, so multi-access edge computing, where you can make the processing of the IQ samples to make sense out of it. So it's complete offloading, and it's not going to really require any additional features on the Gnode B itself, just that external entity that would do the processing. So complete offloading process that has its own merits in terms of what hardware is needed on the base stations and so on. The second one is when you have all the capability within the base station itself. So you are not having an external edge computing capability or anything like that. You are using the samples that you get. You are doing all the processing, say, in your DU or your CU. So what is the drawback? The drawback is that now your base station will have to have this additional capability that can do all the processing. Advantage is that now you will not have to redirect your samples to an external capability. You can do all those processing within the base station itself, and that is going to reduce your latency. Okay. We don't have to stick to these 2 extremes. It could also be that you could have some of the processing done in the Gnode B, and more complicated processing can be redirected to an external client. Okay. So that is the hybrid approach where you have probably you're going to get the benefits of both the approaches. So you don't have to do all the processing externally, or you don't have to do all the processing within the base station itself. Now, as I said in the first couple of slides, you don't have to stick to one of them. In fact, it's always better to take advantage of both of them because in a general system, the first approach, which is the non-intrusive approach, could be used as a trigger to do the intrusive approach. So as I said in the earlier slide, intrusive approach is very powerful. However, it also is going to cause degradation to your communication system. So what could be done is that you could have two different activities happening at the same time, with the first activity triggering the second one as and when there is a detection of the incumbent. Okay, so this is the two systems happening simultaneously, but the second loop or the real-time system only happening when the first system is going to trigger it. So because of this adaptive nature, you will be able to save a lot of resources, and you will be able to do this only when there is an actual presence of an incumbent. You can see that on the right-hand side, the probability of detection and probability of false alarm, this is just as a measure of how well you are sensing, would increase as you increase the sensing resources, right? So as more and more slots are devoted for sensing, you would have you would have a better performance. So you would actually allocate more resources only when the outer loop is going to trigger the inner loop, so that you can preserve that for communication and use it only when there is a need. Now, G node B is just a small portion of the whole network, right? And the fact that the sensing that is done by one G node B could be affected by several different aspects, several different environmental conditions, is something that we need to take care of. And if you are able to get the information from multiple G node Bs, then you are also able to fuse them together. You are also able to get a holistic view of what is happening within a big geographical location. So for example, if you have an aerial radar that is flying, you may be able to sense using one of the G node Bs, and that G node B could now collaborate with the neighboring G node Bs, send a signal saying that, okay, there is a likelihood that an incumbent is going to arrive. So this network as a sensor, that's the key idea, where you are using multiple G node Bs, each with the capability of sensing its surrounding and combining them using some sort of data fusion that is happening at the network, that are happening at the geographical level. The accuracy of the sensing obviously would require how fast you are able to do this and how collaborative these sensors, these different systems are. Fortunately, 3GPP itself has defined all these interfaces. For example, the XN interface is the interface that would be used to communicate different G node Bs. Okay, so some of the key detection and estimation parameters. Yeah. Detection, as I said, the probability of detection, probability of false alarm, sensing latency, right? So how long does it take for the G node B and the network itself to sense something once you detect an incumbent? Number of G node Bs that are needed, because this is going to be a cluster of G node Bs doing collaborating and sensing an incumbent, and the area that can be sensed. So all those things are going to be an important aspect when you do the performance evaluation of such a system. And keep in mind that we may or may not be able to do the estimation part depending on the kind of incumbent, because there are sensitivities associated with the federal systems. You may not be allowed to, you may not be you may not want to do the velocity, position, and the nature of the incumbent, because if it sensitive incumbent, those things are not something that you would want to do. So that is the idea that we want to use for future spectrum sharing studies and spectrum sharing programs. And some of the key takeaways is that the ISAC architecture, which is the integrated sensing and communication architecture that is defined in 3GPP, which will become a key part of 6G, can be used for this incumbent sensing, and it's going to be very powerful, which would eliminate the need for having an external ESC kind of capability. We also need platforms that can integrate RIC and MEC, because as you see in the slides that I showed you, there is a close coordination that is required between RIC and MEC, so that you can use your information that you collect from the RIC to trigger your MEC processing. And that kind of close coordination can happen when you have a platform which is like a combination of these two different aspects, RIC and the MEC. And in many cases, I think it is also important to have this programmability, right? Programmability of the switches, because you will be required to switch between different modalities of sensing based on the information that you acquire. So those are, I think, some of the things that we can incorporate in the next generation, as well as next versions of our standards, be it ORAN specification or 3GPP, that would really enable us to do spectrum sharing in a very efficient, very dynamic fashion.
Thank you. So
okay.
we can take a quick question and we have. I have a question. So in terms of the implementation, how things are progressing, some of these integration with MEC and RIC and...
Yeah, so we have a very robust internal R&D program at MITRE, and we are pretty much in I would say that 60 to 70% of the G-node BSS sensor has been completed. So we are able to do this in a realistic fashion, and also we are able to do the detection of some incumbents. I don't want to name the details of the incumbent, but at this point it looks very, very promising.
Excellent. All right. Thanks again.
Yeah.
Small gift for you.